This video is for Titan Building Block 4M cam on a Haas Mini Mill 2 at the Pierce County Skills Center, Aerospace Machining and Fabrication. To start off, you can simply take your setup 1 from Titan 3M, right click, copy, and paste it into your 4M cam, and we'd want to delete this slot. Still gonna face 3D adaptive, contour, pocket. Most of this is the same. Let's delete that one, and then we only need one of the chamfers. Going to actually right click and delete this because I have mine all up here. Starting off with your setup, we're gonna have our work coordinate system on the top front left stock box point. Our stock is going to be fixed size box, 2.4 inches in the X, 2 in the Y, 1 in the Z, and just like before, offset from the top 0.03. Post process 4001, program comment as usual, and number 1 for our work offset to make it G54. Your first facing operation, everything should be fine. Geometry, don't have to select anything, click OK. You should have one path. 3D adaptive, still at 6,000 RPM. The cutting feed rate is a little bit slower on this part. One of our end mills is getting a little worn out, and the regular mini mill is just having trouble. The super could handle it, so we're going to reduce our feed per tooth from 7 thou to 6 thou, and that will give us 108 inches per minute, 6 thou feet per tooth. Our lead in and lead out is still going to stay at 100 inches a minute, ramp 30 inches a minute, plunge 30 inches a minute for 5 thou feet per revolution. Geometry, we are still going to do rest machining from previous operations. Heights, we want to overshoot the model bottom by negative 25 thousandths. Passes, tolerance is fine at 4 thousandths. Optimal load 0.1125. That's a percentage of the end mill. If we click on edit expression, we're running 30% of our tool diameter. Machine cavities, that's fine. Climb milling is fine. Maximum roughing step down 0.8. Fine step down 0.08. 10 thou stock to leave, axial and radial. Linking, we want stay down level to be most. Our lead in and lead out transitions should be fine, and we're going to increase our ramping angle from 6 degrees to 8 degrees to save a little bit of time and be a little bit more aggressive with our ramp entry. Okay. Remember, the 3D adaptive takes a little bit of time to load, and our toolpath should have some 3D adaptive on the outside, inside, helical ramp, one pass to clear that little shelf. Next operation is going to be a 2D contour finish pass to clean up the outside of the part all the way down to the bottom. So that's still tool number 2, 3/8 flat end mill. This should be the same from our previous Titan building blocks. 6,000 RPM, 80 inches per minute. For our feed rate, geometry is going to be the bottom selection, arrow on the outside, heights, this is all standard, and then our bottom height is going to be -5 thousandths just to overshoot the model by 5 thousandths or the selection. Passes, this should also be fine. We want to have our cutter compensation to be in control, not in computer. That's going to base the position of the tool off of the actual diameter, not just the center of the tool programmed in Fusion. You might need to change your compensation radiance allowance to 0. Finish feed rate 80 inches a minute. Repeat finish pass. Go around twice for a spring pass. And this should all be fine. We're just going to plunge straight down, so it really doesn't matter. Do believe there is one thing I forgot in the 3D adaptive, and that's going to be changing our minimum cutting radius to 10 thousandths. This will allow us to get into the corner of the inside pocket of the triangle. Next operation is going to be a 2D contour. You can simply take this operation and duplicate it, and it's the exact same thing except for it has different geometry, 1, 2, 3, and the bottom height is at 0 offset because we just want to go right down to that edge. It's going to clean up the floor and the wall at the same time. Also using cutter comp in control. Click OK. 2D pocket on the inside. Same tool. Same from before. 6,000 RPM. 3,000 feet per tooth. That's 54 inches a minute. Plunging at 18. Geometry is this bottom pocket. Heights basically 0. We don't want to go past the bottom of that selection. So this is the standard. Passes. All of this should be fine. Leaving 6,000 radial stock so we can clean up the walls in a separate operation. Linking. Plunge. We don't need a helical ramp. We're just going straight down. Click OK. 2D contour inside. This is going to clean up the wall. 6,000 RPM, 54 inches a minute, 3,000 feet per tooth. Lead in, lead out 40, ramp 30, plunge 18. Geometry. Bottom selection. Heights, the standard, no offset on the bottom. Passes, we're going to be cutter comp in control. Repeat finish pass. Stock to leave, we're going to leave 5/10 axial to keep our end mill off the bottom of this floor so it's only touching on the side. Linking. Everything in here should be fine as is. Our next 3 operations, spot, drill, and tap, are identical to Titan 3M. So we should be spotting at 1500 RPM, plunging down at 20 inches a minute 3 times, and then have a depth of -103. Cycle type, drilling rapid out. Drilling is going to be 3000 RPM, plunging at 30, retracting at 40. Geometries is selected faces. Heights going to be hole bottom, drill tip through bottom. Cycle type chip breaking. Tapping 1032 tap. Make sure you select the correct tap. 1032, it's the 0.19 by 0.03125 right hand tap. Flood coolant 1500 RPM. Select the geometry. Bottom height should be whole top negative 0.45. Cycle type right tapping. Click OK. And then let's make sure that we hold down control, select our tap, drill, and spot. Go to a front view and we can see that our drill is deeper than our tap. And also our spot drill does the proper countersink. Okay. The next operation is going to be a 2D contour with a new tool. It's a slot mill. It's going to be used to come in and scoop out this arc or radius on the side of the part. We need to first create a new tool for that operation. Tool library. You're going to select your Haas library. New tool. It's going to be a slot mill, and I'm going to switch over to the one that I already have made. Tool numbers, Titan 4M library, slot mill, edit tool. So starting at the first tab, the description is going to be 1.5 times 1/8 slot mill. This is also known as a woodruff cutter or a key cutter. Cutter, slot mill, 16 flutes, high speed steel, no through cooled toolant. It's going to be clockwise spindle rotation, that's very important, and it's in inches. Diameter 1.5. Press tab to go to the next item, which is shoulder length. That is 0.5. Shaft diameter over here. Excuse me. Flute length 1/8 of an inch, 0.125. Body length 0.7. We actually measured it after we set it up in the tool holder. How much of that tool is sticking out away from the collet. Shaft diameter is 1/2 inch. Quarter radius is 0. So once again, diameter 1.5, corner radius 0, body length is going to be 0.6. I need to make my window a little bigger. There we go, I couldn't see that. 2 inches for the overall length. This was actually 0.7. Shaft, don't worry about that. Holder. It technically is a Cat 40 ER32 holder. You don't really need to program the holder for this operation. We don't have a lot of tight spots and need to worry about collision detection. Feeds and speed, it's going to be 2000 RPM. Cutting at 40 inches a minute. Lead in, lead out is going to be 40, ramp 15, and plunge 15. So that's 2000 RPM, 40 inches a minute. Post processor, tool number 6. It's going to be a 1.5 inch slot mill by 0.125 thick, flood coolant, live tool, click OK. And now that tool is in the library. You're going to go to 2D contour, select the tool number 6. The 1.5 inch slot mill, 2000 RPM, 40 inches a minute. This should already be plugged in and good. Geometry is going to be these 3 inside bottom contour selections. Heights, this is all the standard. Bottom height is selected contours. Top height is model top. Feed height, model top 0.2. Retract height is model top point. Yeah, it should be like 0.3. Gets bigger and bigger and bigger as it goes up. Passes. Cutter comp is going to be in control. Finish feed rate 40, looking good. Linking. You want to make sure that when this comes in, it comes out all the way and doesn't just lift up and gouge apart. So we have a horizontal lead-in radius of 0.15, 90 degrees, linear lead-in distance 0.3, vertical lead-in radius 0.15. Click OK. And I'm just going to simulate this right now without the stock, and I'm going to go slow and really watch what's happening. Pulling out, pause it, make sure it's going away from the part, and then lifting up and over. This is also kind of cool. You can click on show points and we can actually where are the points? I don't know, there's supposed to be little black dots right here where you can see your simulation and go to that very specific spot. But I have no idea why they're not showing up. You can also click and drag and just kind of scrub through this. Speed it up, slow it down. Close. And then our last operation is going to be our edge brake chamfer. Tool number 9, 4,000 RPM, 64 inches a minute. Same as before, geometry, inside edge, outside edge, and these 3 little bottom edges. Height should be the same as usual. And then for our chamfer dimensions, the chamfer width is still 0.01. The tip offset, we're going to make that a little bit bigger, make it 0.08. And we're going to go less clearance so we can get our chamfer mill right in here in a nice chamfer on that edge. Okay. Simulation, model off, simulate, stock, change this to tail, facing, very light cut, 3D adaptive, finish pass, contour, pocket, contour, spot drill, drill, tap, tap, tap. I'm going to pause it. Transparent. Just going to make sure again that our drill bit depth is deeper than the hole. I think we might need to go in on mine. I need to make this hole a little bit deeper. So back to model. I'm going to find my hole, right click, edit feature. Depth of that hole, I'm going to make it 0.5. Go back to cam. Going to regenerate my drilling and tapping. And now I got plenty of clearance between bottom of the hole, bottom of the tap. Control G. If you ever get this message, one or more operations do not require regeneration. Do you want to regenerate the operation anyway? You go ahead and click no, so you don't regenerate those 2 operations that are already generated. Okay. Back to our simulation. Facing. Adaptive. Hinge pass. You can also click here, just go straight to that. Spot drill, drill, and tap. So we've got plenty of clearance for the tapping operation. There's our key cutter, our slot mill. And we're going to finish with our chamfer. Okay. Zoom in, looks good. Close. Tool numbers should be tool 1, tool 2 for the 3/8 flat end mill, tool 3 is the spot drill, tool 4 is the 177 drill, tool 5 is the tap, tool 6 is going to be the 1.5 inch by 1/8 inch slot mill, and tool 9 is our chamfer. Post process. Make sure you're using the right post processor. We want to use the pre-next generation control when using the regular mini mill and the next generation control for the super mini mill. And for right now I only have one of those key cutters that I have in this file. So everybody will be using the regular mini mill with the pre-next generation control, program name and number, and comment. Make sure that G187 is on. I don't know where it's at. Honestly, probably you guys don't even care what G187 is. And it should be back. Oh, that's because I'm post-processing to the plasma table. So it looks like I accidentally hit the scroll wheel on my mouse. Now G187 is on it. Yes, that is basically it has to do with our roughing operations. Post. I'm going to save this to my desktop. You'll save it on the flash drive. G code tool 1, 2, 3, 4, 5, 6, and 9, starting off with facing operation. 3D adaptive, that's where most of our G code is going to live. To contour, pocket, contour, spot, drill, tap, 2D contour with the slot mill, and finishing with a chamfer. And that is it for Titan building block 4M.